Alright, hello class. In this video we're going to be looking at the introduction to the next module. So we are going to be leaving derivatives behind for a little bit and start focusing on antiderivatives. These are also known as integrals, okay, but we'll talk a little bit more about that as we move along, but I'm just saying that in case I slip up and use that term as well. They're interchangeable. And so what antiderivatives are all about, okay, is essentially that step we always take in math classes where once you learn one direction, you always want to learn how you get back. So for example, we've been talking about derivatives and applications of derivatives this whole time, talking about how we get from f to f prime, right? And we do that with the derivative. Okay, what an antiderivative is how we say go back. Say we start with a derivative and we want to get back to the original function. That's where the antiderivative comes in. All right, and you might think, well, hopefully, or you would think that we might have a better name for that than antiderivative. But it's kind of fitting because we are undoing the derivative to get back to the original function. Okay, and that's also why integrals pops up as a term we use. Less syllables there than antiderivative over and over and over again. But that's what we're going to be focusing on here. So while we are leaving derivatives behind for a little bit, we still need to know our derivative rules really well, because all we're doing is reversing them here. Okay, so that's it. So if your derivative rules are really ingrained and well known in your head, you should be fine. Okay, all you're doing now is thinking backwards. However, there are situations where the thinking backwards can be really difficult. I think of logs, for example. Logarithms are the reverse of exponentials, and it can be kind of difficult to think backwards in that sense. But that's really what we're doing, is the thinking backwards. Okay, so let's start with the definition. Given a function, a little f of x, if capital F of x is a function where capital F prime of x is equal to little f of x, then capital F of x is an antiderivative of little f of x. This word here, an antiderivative, is very important here. Okay, let me give you an example. I think this is kind of a little brain melty as far as how this is worded and how we define it. But basically, an antiderivative of little f is going to be any function. If we take the derivative and get back to f, that will be its antiderivative. So take, for example, a little f of x equal to 2x. Okay? Now, I can find a function, capital F, whose derivative will be 2x, right? If we choose capital F of x to be x squared, right, then capital F prime will be 2x, which is little f of x. All right, so capital F is an antiderivative of little f. Okay, and the reason we're saying an antiderivative here is because if we look at, say, a capital G of x equal to x squared plus 10, well, this g prime would also be 2x. Okay, so capital G is also an antiderivative of 2x. Okay, and in fact, we can make as many antiderivatives of little f as we want. We already found x squared plus 10. We could do x squared minus 100. We could do x squared plus pi, x squared minus e, x squared plus the square root of 99, on and on and on and on and on. All of these are going to be antiderivatives of 2x. Right? And all of these will become, or will be antiderivatives of 2x because the derivative of a constant is 0. So every antiderivative of 2x is going to look like x squared plus a constant. Okay? So that is what we typically look for when we find the antiderivative of a function. The antiderivative is a family of functions that represent every antiderivative of the function we're looking at. Okay? So what we're actually showing is a representation of what every antiderivative will look like. Okay? So in this case, the antiderivative of 2x will be x squared plus c, where c is an arbitrary constant. So whenever we're looking for antiderivatives, this is what we want to end up with. It's always going to be some function plus c, because what we're doing is basically showing the form that every antiderivative, in this case of 2x, will look like. Every antiderivative of 2x is going to look like x squared plus c. That c could be anything. It could be 0, 10, negative 100, pi, negative e, square root of 99, right? Negative a million, plus a million, whatever, okay? There's an infinite number of possible antiderivatives, okay? Now, sometimes we will care about a specific one. We'll talk about that a little later, but the majority of the time when we are finding antiderivatives, we just tack on a plus c because that gives us the representation of every possibility. Okay, and that's what we're looking for here. All right, now as I talked about before, the antiderivative is often called the indefinite integral, and I put indefinite in parentheses here because usually we only specify, or at least I only specify when it's a definite integral. We'll talk about that later. But the antiderivative is often called the integral with this following notation. We often use this notation. It's the integral sign, okay? So what is the integral sign? It's basically an elongated s. Okay, that's basically what this integral sign is. It's an elongated s, and we would write the integral of 2x dx, okay, is equal to x squared plus c. All right, so this is the notation. So here's the integral. Right, here's what we would call the integrand. That's just the thing being integrated. So the integral of the integrand dx. Now, this notation is going to look a little weird right now, and we'll talk about in a later section where this notation comes from. It actually makes a lot of sense. This s is for sum, okay, and we'll talk about that later on. And this dx does show up naturally as sort of a delta x like it does with derivatives. But for right now, what we need to know is that this tells you the variable of integration. Right? Are you integrating with respect to x? Are you integrating with respect to y or z or w or v or t? Or okay, that's what the dx tells you for right now. It also gives you a sense of what an integral is doing. It is doing something opposite, right? If you think about what a integral does, if you have dy dx, right, and you take the integral of it, you'll notice that these dx's kind of cancel each other out. And that's essentially what we're doing with an integral. Also, with the derivative, we do dy dx, but with the integral, we do the integrand times dx. I think this gives a sense of how an integral works. We're multiplying by dx instead of dividing by dx. We are doing the opposite of what the derivative does. Right? And that's going to be the pattern this entire time. The integral does the opposite, in the opposite order of what the integral does. Right? So I can't emphasize this enough. The integral does the opposite of what the derivative does, and in the opposite order. Right? So we have the power rule for the derivative. Right? If we have x to a power, okay, what does the power rule do for the power rule in the derivative? Well, one, it multiplies by p. Okay, so we'll say step 1 multiplies by p. So I'll say multiplies by the power. Okay, so we'll have p times, and then raises x to the power minus 1. Okay, so we'll have p times x to the p minus 1. Okay, on the other hand, if we have the integral of x to a power dx, well, the integral should do the opposite, right? In the opposite order, right? So we'll go reverse through this step. So here, step 1 will raise x to the power plus 1. So that's what I mean by opposite. We're raising x to the power plus 1. So it will be x to the p plus 1, then 3, whoops, not 3, 2. Now we multiply by the power. Well, now we're going to divide by the new exponent. All right. So we change the power by plus 1 first, and then we divide by it, and we get a plus c. All right, so that is just going on this idea that the integral should do the opposite of what the derivative does, but is that true? Does this actually work? Well, let's try the integral of, let's say, x to the 5th dx. So this idea says, okay, we take x, raise it to the 5 plus 1, and then divide by 5 plus 1, and then we add a plus c. Okay, so we will end up with x to the 6th over 6 plus c. Now, is this the antiderivative of x to the 5th? Well, a quick way to check that is we just differentiate what we got and see if we get back to here. Right, if we differentiate x to the 6th over 6 plus c, okay, we'll get, well, the derivative of x to the 6th over 6 will be 6x to the 5th over 6, and then the constant goes to 0, and so we end up with x to the 5th, which is exactly what we started with. Okay, so it turns out this rule actually holds water. Okay, the integral is always going to do the opposite of what the original derivative rule does. Okay, so this is the power rule. Okay, we have the following exponential rule that the derivative with respect to x of e to, say, the rx, right, some constant times x in here, is r times e to the rx. Right? So what does this do? Step 1, it multiplies by the constant, and then it's just itself. Right? So step 1 multiplies by the constant in the exponent, and 2, it's that constant times itself. Okay? Well, so the step 1 times itself, right? The itself part is going to stay the same when we go to the integral. So when we do the integral of e to the rx dx, we still get e to the stuff, right? But now, instead of multiplying by the r, we should divide by the r. Plus c. So basically, any time a derivative multiplies, an integral will divide. And vice versa. Anytime a derivative divides, the integral will multiply. Okay, it's just whatever one does, the other does the opposite. So this is actually the exponential rule, okay, for e to the rx, not e to anything. We don't have a reverse chain rule just yet. We'll get there, okay, but this is that general exponential rule. Okay, what about logs? Okay, so for logs, well, we have that the derivative with respect to x of the natural log of absolute value of x is 1 over x. I'm using the absolute value of x to get the whole domain. We talked about that in the log rules for derivatives before. Okay, well, if this is true, there's not much work to do to reverse this, because this will tell us that the integral of 1 over x dx is simply the natural log of the absolute value of x plus c. Okay, we just reverse things when we set up the integral. Now, this integral of 1 over x, the reason it gives us ln of x, or absolute value of x, one is because we were reversing the log rule, but two, if you tried to use our normal power rule with x to the negative 1, with our normal integral rule, we'd get negative 1 plus 1, negative 1 plus 1. We'd get x to the 0 over 0, which is garbage, right? But that's okay because we already have the ln rule that we're swapping around to get here. All right, what about other bases, right? Base is not equal to e. Well, the derivative of b to the x is still itself times the natural log of b. And if we put in an r, we'd have an rx there as well. Okay. So I'll do that in the next step here. So when we do the integral rule, well, the integral of b to the x dx, well, we do the opposite. It's going to be itself, but instead of multiplying by the natural log of b, we should be dividing by the natural log of b. Okay. So there's the general b to the x rule. And for log base b, the derivative is 1 over x times the natural log of b. Well, that tells us that if we, and this one's going to be a little different, if we have 1 over x times the natural log of b, we could say that that's log base b, or we also have the same idea here that we can factor out constants, and 1 over ln b is just a constant. Okay, and so we end up with, and actually, that should be absolute value there. Sorry about that. And based on what we have before, the integral of 1 over x is just the natural log of absolute value of x plus c. Okay, so does this end up being the same thing as this, log base b of x? Well, yes, because one of our log rules is that if we have the natural log of absolute value x over the natural log of b, we can rewrite that as log base b of the absolute value of x plus c. I will admit this one doesn't come up as often, and partially it's because you can just do this. You can kind of change things around and make it, you could even do that here, ln absolute value of x over ln b, and factor out the ln b. Okay, but here it is for posterity's sake. Okay, and as I mentioned, to complicate this one a little more, if you had b to the rx, it would be r times ln b times b to the x, meaning that the integral of b to the rx dx will be, well, it's going to be itself but instead divided by r times ln b. Okay, so let's test this one out with an actual value here. Let's say I want the integral of, say, let's say 1.5 to the 2x. Okay. Well, based on this, the integral is going to be itself 1.5 to the 2x all over 2 times the natural log of 1.5 plus c. Okay. Now, I'm going to rewrite that as 1 over 2 ln 1.5 times 1.5 to the 2x plus c, and then I'm going to test this. All right, and I'm not going to rewrite it again. I'm just going to take its derivative. So the constant comes along for the ride. The derivative of 1.5 to the 2x is going to be, well, 2 times the natural log of the base, 1.5, times itself, 1.5 to the 2x. So the 2 ln 1.5 and the 2 ln 1.5 cancel, and we're left with a 1.5 to the 2x, and there we go. All right, now once we get all these rules rolling, I am just going to look at some examples, okay? So don't fret too much if you think we're spending a little too much time on the abstract stuff. All right, next up is the trig rules, or are the trig rules, I guess I should say. We have that the derivative of the sine is cosine. So it stands to reason that the integral, okay, if we just reverse this, that the integral of cosine dx will be sine of x plus c, and that's true. Okay? On the other hand, the derivative of cosine of x is negative sine x. Now, I'll admit, you often won't see, sometimes you will, but for the typical rule, if I want sine of x dx, I want its integral, we're going to have to move the negative to the other side. All right, because if we move the negative over, the derivative with respect to x of negative cosine x will be positive sine x. And that's what we're looking for. We're looking for the function whose derivative will be sine of x. In this case, it's negative cosine x plus c. Okay, so these work opposite. And I think this is where people have a lot of trouble, because the integral rules for trig functions work opposite of what we're used to. Cosine goes to positive sine in this case. Sine goes to negative cosine. Okay, but remember, we are reversing, we're doing the exact opposite of what the derivative does when we're finding the integral. Okay. Next up, well, the derivative with respect to x of tangent is secant squared x. Okay, so how we turn this into an integral rule is that secant squared x dx is tangent x plus c. Okay. Similarly, the derivative of secant of x is secant x tangent x, and that gives us an integral rule of secant x tangent x dx. That integral is simply secant x plus c. So these might seem a little weirder than what we've dealt with, but all we are doing is reversing these two to give us the new integral rules. So notice, this is not giving us integral rules for secant and tangent all by themselves. We'll need a little more work to get those. In fact, in the next lesson, we can talk about the tangent one. Secant, you probably have to wait till Calculus 2 to figure that one out. Maybe not. We might have the tools for that, but typically we focus on this one in Calculus 2. Okay. And then the ones that give us the negatives, we can make with pretty much the same patterns. Right, because the derivative of negative cotangent x is cosecant squared x. So that means the integral of cosecant squared x dx is negative cotangent x plus c. And similarly, the derivative of negative cosecant x is cosecant x cotangent x, which tells us that the integral of cosecant x cotangent x dx is a negative cosecant x plus c. So notice for the cosecant and cotangent, the cofunctions here do still give us a negative. Okay, it's the sine and cosine that flip for the normal, for the integral, whereas here, here they don't. Okay, so again, these can, I understand that these can be confusing. However, with some practice, hopefully it will start to get a little better. All right, so we have a bunch of other general rules that still hold, right? We have the sum rule, which basically says that if we have the integral of a sum of f of x plus g of x, we can instead take it term by term. Right? If we can take things term by term for derivatives, we can do it for integrals as well. We have the constant multiplication rule, right? That if we have an integral of c times f of x dx, we could instead move the constant outside to get the constant times the integral f of x dx. So we can do that. And we also have a constant multiplication rule for the inside. Right, so the inside constant multiple rule, what is that talking about? Well, we've already kind of looked at it in terms of e to the stuff. So if you have f of some constant times x, right, and you take the derivative, well, since it's just a constant, by the chain rule, you get a constant on the outside times f prime of cx, right? So it turns out that if you are instead integrating with a constant on the inside, so you have little f of cx dx, instead of multiplying by the c, you'll be dividing by the c, and it will be times the antiderivative of cx, plus, I probably should have used a different letter there, plus the arbitrary constant, I'll use d here. Okay, so the inside constant multiple rule, you can think of, you multiply by that constant on the outside for derivatives, so you'll be dividing by it for integrals. To give you an idea of what I mean by that, think of the integral of cosine of 2x dx. By this rule and the other rules we've looked at, this should be 1/2 sine of 2x plus c. Is that the actual integral? Well, let's differentiate and find out. The derivative of 1/2 sine of 2x will be 1/2, and the derivative of sine of 2x will be the derivative of 2x, which is 2, times cosine of 2x. So the 2's cancel, and we get cosine of 2x. So yes, that does line up with this. Okay, so this is a rule a lot of people forget, but it's really important to finding the right antiderivatives. Okay, this idea that you'll be dividing by that constant. All right, from here, we're just going to look at a bunch of examples because we've gotten all the rules out of the way. So let's just crank out some examples here. Okay, so let's look at our first example, right, which will be the integral of 3x to the 5th minus 5x to the 9th. So remember, we're integrating. So like before, the constants come along for the ride, so that 3 will come along for the ride, and we can do these term by term. So then it will be the integral of x to the 5th. So remember the power rule for integration will be x to the 5 plus 1 divided by 5 plus 1. Okay, and there's the integral of x to the 5th. Now eventually I'm going to kind of jump to what these things are, but for right now we can afford to be a little more deliberate here. It'll be minus 5 comes along for the ride, and then the power rule for integration, or for x to the 9th, will be x to the 9 plus 1 all over 9 plus 1, then our plus c. Okay, so I have 3 times x to the 6 over 6, and so the 3 will cancel with the 6 and leave a 2. And then we'll have minus 5 times x to the 10th over 10, and once again here that 5 will cancel with the 10 and leave a 2, and so our answer here is x to the 6th over 2 minus x to the 10th over 2 plus c. And if we wanted to quickly check our answer here, if we took the derivative of x to the 6th over 2 minus x to the 10 over 2 plus c, we would end up with 6x to the 5th over 2 minus 10x to the 9th over 2 plus 0, which will be 3x to the 5th minus 5x to the 9th, and there we go. That's it. Okay, so a lot of these do come down to, just like with derivatives, knowing the rule, applying the rule. All right, for our next example, let's look at the integral of 5 over t squared plus 4 times t squared plus 1 dt. Now, I guess we haven't really talked about some of the things that we'll look at here. Okay, but here's my advice. We're going to rewrite this piece as a power. So we're going to approach this often like we do with derivatives. Now notice, we don't have a quotient rule or backwards quotient rule yet. So don't start trying to do some sort of quotient rule here. What we're going to want to do is rewrite this integral as 5t to the negative 2 plus 4t squared plus 1 dt. Now, we didn't really talk about the integral of a constant, okay? But you can always think of a constant as 1 times t to the 0. And hopefully that will sort of get you to where this should be, okay? Because now it's just power rules, right? It'll be 5t to the negative 2 plus 1 over negative 2 plus 1, okay, plus 4 times t to the 2 plus 1 over 2 plus 1, plus 1, then times t to the 0 plus 1 over 0 plus 1, and of course we'll have a plus c. What I'll mention is once you take the integral, once you start integrating, your integral sign can disappear. You can drop it there, but then it gets replaced with a plus c. All right, so this will be 5 times t to the negative 1 over negative 1 plus 4 times t cubed over 3 plus 1 times, this will simply be t over 1 plus c. So the integral of 1 is, in this case, t. That makes sense because when you differentiate t with respect to t, you get 1. Okay, so a constant is going to integrate up to a constant times x, or a constant times t. All right, and if we make this look a little nicer, we'll get negative 5t to the negative 1 plus, all right, this is 4/3 t cubed plus t plus c. And there we go. There's our final answer. Yes, you can leave it like this, or you could rewrite it as negative 5 over t if you prefer. Notice I moved the fraction outside, and often that's how I write these. You'll notice in future examples, instead of t cubed over 3, I often write it as 1/3 t cubed, just to keep the constants outside. There's no right or wrong way to write these things in that sense. It's just my personal preference. All right, so next example, let's look at the integral of 4 root x minus 4 over root x. And once again, for the integrals, for right now, until you get a better handle on the patterns, I would just rewrite these as exponents, right? Square root of x is x to the 1/2, okay? Dividing by root x will be x to the negative 1/2. Okay, now we should expect to get a square root something here, right? Since we already have the derivative of the square root of x is 1 over 2 root x, we would expect that the integral of 1 over 2 root x dx to be the square root of x. Okay, which we don't quite have that, but we'll have something close. So let's just go ahead with it. This will be 4 times x to the 1/2 plus 1 over 1/2 plus 1. So to kind of simplify our lives, 1/2 plus 1 is 3/2. So this will be x to the 3/2 over 3/2 minus, and then here, negative 1/2 plus 1 will be x to the 1/2 over 1/2 plus c. Now, I want to show something very specific here. This will be 4 times, whenever you're dividing by a fraction, you're going to invert and multiply. So this will be 2/3 x to the 3/2. And the reason I'm showing this is because notice, no matter what your exponent is, you're always multiplying by the reciprocal. So if we go back to the previous example, so here we have t cubed multiplied by the reciprocal of 3. Right? This is 3 over 1. We're multiplying by 1 over 3. You're always multiplying by the reciprocal. We think of it as dividing, but with these fractional exponents, that's going to make this very nice, or at least quicker in some cases. Because here, instead of dividing by 1/2, you're multiplying by 1 over 2. Right? So you're always multiplying by the reciprocal. So that's going to speed us up as we go forward. Okay? So we're going to get 8/3 x to the 3/2 minus 8 x to the 1/2. And I would just leave it like this. Okay? Or you could change that to x under the square root if you want. But I would just leave it like that. All right, next up, let's look at the integral of 3x plus 1 all times 4 minus x dx. Now, we don't have a backwards product rule yet. You will get one in Calculus 2, so we can't do that here. In fact, once you learn what the backwards product rule looks like, you won't want to use it anyway. So sometimes, especially now when we don't have a lot of our robust rules, and just for the record, Calculus 2 is the class that really focuses on integration. And so that's when you learn all of these more advanced rules like backwards product rule and so on. We will talk about a backwards chain rule in this class, but in cases like this, it's easier to just multiply this stuff out and simplify it down so that it can just be power rules. Okay, so once you multiply this out, you'll get the integral of 12x minus 3x squared plus 4 minus 4x, and we can simplify this, right, to get the integral of 8x minus 3x squared plus 4 dx. Okay, and now we integrate. All right, so we'll get 8 times x squared over 2 minus 3 times, in this case our exponent is 2, so it'll be x cubed over 3, and then the integral of a constant is that constant times x. Right, so we end up with 8 times x squared over 2 minus 3 times x cubed over 3 plus 4x plus c, which simplifies to be 4 x squared minus x cubed plus 4x plus c. Okay, and there we go. All right, this is going to be a similar example because we don't have a backwards quotient rule. Okay, and this is this sort of nasty function with a fraction. We can't just do integral of the top over integral of the bottom. If it doesn't work for derivatives, it's not going to work for integrals. So what can we do? Well, in this case, we just need to do some algebra. We need to start by factoring. All right, so we can factor an x out of the top, and we'll be left with an x squared minus 9x plus 20. And this whole thing's still over x minus 4 dx. And this thing, the x squared minus 9x plus 20, should factor. We want factors of 20 that will sum up to be negative 9. So negative 4 and negative 5. So negative 4 and 5, negative 5 come out to be positive 20. Negative 4 minus 5 is negative 9. So we end up with the integral of x times x minus 4 times x minus 5 all over x minus 4. And there we go. The x minus 4's cancel. Don't forget our dx here. And so now we have the integral of x times x minus 5 dx. And so now I would just do one final distribution to get the integral of x squared minus 5x dx. And then we can integrate. Integral of x squared is going to be x cubed over 3, then minus 5. X to the 1, its integral will be x squared over 2 plus c. And that's it. We could leave it like this. I would personally write it like this: 1/3 x cubed minus 5 halves x squared plus c, but that's just personal preference. Okay. And yeah, there we go. So yes, sometimes you may have to do a little algebra before you can do the calculus. That should probably not be surprising based on how this class has gone so far, but there you go. All right, Dr. D, I hear you say, do some trig problems. All right. Request oblige. For next couple examples, we'll be looking at some trig stuff, some E stuff, that kind of thing. So let's say we have cosecant squared plus 1. So cosecant squared theta plus 1 d theta. And here we just apply the rules. The integral of cosecant squared, okay, is that's going to be negative cotangent theta, right? Because I want the trig function that's going to differentiate to give us cosecant squared, so that will be negative cotangent theta. Then the integral of 1 with respect to theta should just be theta. Then we'll have plus c. And just to double check this, the derivative with respect to theta of negative cotangent theta plus c will be, well, negative times the integral, or times the derivative of cotangent theta, which will be negative cosecant squared theta, plus the derivative of theta with respect to theta, that will be 1. Then the derivative of a constant is 0, and so we'll end up with cosecant squared theta plus 1, and it checks out. All right, here's another example involving trig where some algebra is going to be required. Again, we need to change the way this looks, because as a fraction like this, we won't be able to approach it. And even if we could do the integral of just the top and the bottom, this sine squared is going to cause us problems. So whenever you see one like this, I would recommend splitting up the fraction, right? So that you have a 2 over sine squared x plus 3 cosine x over sine squared x. Now, say this 2 over sine squared x, well, 1 over sine squared x is going to be cosecant squared x, right? So this, the 1 over sine squared, I could rewrite this, well, it's really a 2, but 2 times cosecant squared x. Now this one's a little trickier, okay? I could say cosine times cosecant squared, but that's not really going to help us. What will help us instead is if we think of it this way. This is 3 cosine over 1 sine of x times 1 over another sine of x. There's nothing saying we can't do this. Split up that sine squared in this way with multiplication. And now this is cotangent and this is cosecant. Right? I'm forgetting my dx's here. That's not a good practice. All right, so we'll have 2 cosecant squared x plus, this is cotangent, so 3 cotangent x, and this is cosecant. 1 over sine is cosecant. All right, so we have 2 cosecant squared x plus 3 cotangent x cosecant x dx. We have rules for both of these. The integral of cosecant squared is going to be negative cotangent x, and the integral of cotangent cosecant is going to be negative cosecant x plus c. And there we go. Little work to get there, but again, as long as you take it step by step and don't panic when you see trig functions, you should be fine. All right, let's look at the integral of 1 over 2x dx. This one, I'm actually going to just split this fraction up as 1/2 times 1 over x. And the reason I would want to do that is because, well, I know the integral of 1 over x. That's the natural log. All right, so the integral here, the 1/2 will come along for the ride. The integral of 1 over x is the natural log of absolute value of x. And we throw in a plus c. And there we go. Okay, so don't be tempted by this to say this is x to the negative 1 and do the power rule. You'll end up with garbage there. Anytime you see a single x in the denominator, you're going to look for natural log. All right, so as another example, okay, so we have t plus 1 all over t dt, that integral. Like before, since we don't have a quotient rule to work with, we're going to split this fraction up. So this will be the integral of t over t plus 1 over t dt. Okay, so I have the integral of 1 plus 1 over t dt. And then now we can integrate. Integral of 1 with respect to t is t. The integral of 1 over t with respect to t is the natural log of the absolute value of t. And then we throw in the plus c, and we've got it. All right, and that's that. Okay, let's look at this integral. So we have e to the 2x minus 5 e to the x plus 4 all over e to the x minus 1. Again, if you ever see a fraction like this, you should expect that things will simplify in some way. In this case, they will, though you might not recognize it immediately. So notice, if instead of e to the x's here, we had, say, y's, right? So if y were equal to e to the x, then y squared would be e to the 2x. Okay, so if we rewrote this in terms of y, we'd have y squared minus 5y plus 4 all over y minus 1. And then in this format, I don't think anyone would have, hopefully, trouble seeing that this would factor. We want factors of 4 that sum up to negative 5, so y minus 1 times y minus 4. Well, we can still do this just with our e's, right? Our y was just e to the x, so we could say that this factors into e to the x minus 1 times e to the x minus 4. All over, leave the denominator alone, e to the x minus 1, and that e to the x minus 1 cancels. So we end up with simply the integral of e to the x minus 4 dx, which is, well, the integral of e to the x is itself. The integral of 4 is 4x. Throw in a plus c, and we're done. All right, so let's look at another example like that similarly. Again, you ever see a fraction like this, expect things to cancel, especially in this class. And in Calc 2, you might, and, well, at least especially in this section. In later sections, it may get a little more complicated, but here we should expect this to simplify in some way, and it will, because what we have here is a difference of squares. This is, of course, t squared, and this is e to the t squared. E to the 2t is e to the t squared, and that means we can do a difference of squares factoring to get that this is the integral of t plus e to the t times t minus e to the t. And that t plus e to the t is going to cancel nicely with t minus e to the t. Okay, so we'll get the integral t minus e to the t dt, and we should be good to go because, well, the integral of t is t squared over 2. The integral of e to the t is itself, and we throw in a plus c, and we're golden. Okay. All right, so I think that's definitely good enough for right now. There is another thing I want to talk about, but I will do that in a part 2 for this video, and that's initial value problems. Specifically, what happens if we want to find a specific c? Okay, how do we do that? And it turns out it's not as complicated as you might think, but it does allow us to do some interesting application problems. Okay, so that's what we will talk about in part 2 of this lecture. I'll see you all then. Cheers.